All right, chapter 18 is on aromatic chemistry. We've thrown around the term aromaticity a few times already, but we haven't strictly defined what it means to be aromatic. So we've seen it in the context of spectroscopy in particular, where we said aromatic protons show up in a certain region. And then I alluded to some sort of ring current going on, but we didn't really touch on it beyond that, really. The interesting thing with aromaticity is that for a long time it was very, very poorly defined. When you think of aromatic, what do you think about? Smells, right? So the old definition alluded to smell, right? So we think of something being aromatic as being very fragrant. It's not always true, though. Oftentimes the most fragrant compounds in chemistry are esters or aldehydes or things like that. Oftentimes the really, really stinky things have thiols. Using smell as an indicator is really terrible. We're not very good at it. So we need to come up with a new definition of what it truly meant to be aromatic. Do you have a question? No? All right, so the modern definition is slightly different. The modern definition says that aromatic compounds are planar ring systems with 4n plus 2, and I'll put this in quotes because we'll talk about that later, pi electrons that are delocalized. The most common aromatic system we see is benzene. Benzene's 90% of the time what we're talking about when we're talking about something that's aromatic. But there are a lot of other molecules that also display the same characteristic. One thing I will ask you to do is to study some of the basic nomenclature at home. We'll review a little bit of it. So the nomenclature I want you guys to review at home is review numbering, review the priority systems, things like that. And I'll post a Khan Academy video to do that. Uh-oh. Study at home. And you're welcome to use the book, too. It's section 18.2. Or watch the video online. But there are a lot of new terms presented in this chapter that I wanted to bring up in class. If we think about benzene rings, just as our most common example of aromaticity, we can think of mono-substituted benzene rings. And for mono-substituted rings, I'll just call this R. Typically, these don't have any sort of special name. If we've got a methyl group on there, we could call it methylbenzene, or occasionally we call it toluene. We don't have to specifically say it's mono-substituted methylbenzene. It's implied that it's mono-substituted if you leave out that mono. But with di-substituted rings, they have very unique nomenclature. So let's say we've got two R groups, and they're right next to each other. Or we could have two R groups where one of the R groups is over here, or we can have two R groups where one is on the opposite side. Now we need to clearly define these positions. Oftentimes people will say 1, 2, 1, 3, or 1, 4, but there's another common naming system that's preferred by most chemists. This first one is called ortho, or you just abbreviate it O. The next one is meta, substituted, or people just abbreviate this as M. And the last one is called para, substituted. So ortho, meta, para simply refers to the positioning for these di-substituted rings. So di-substituted benzene. So these are some new terms we haven't seen. Normally when I name di-substituted rings, I refer to them as being ortho, meta, or para. Occasionally you'll see people just say 1,2 substituted, and that's the same thing as saying ortho. But this is new in the book. The other thing that confused me for a long time is that some of the old names for aromatic substituted systems have stood. Even when we reclassified things using IUPAC rules, they stood. So, for example, when I said if we had a mono-substituted ring with an R group on it, that could be called methylbenzene. The old-fashioned name for it is toluene, and so people use them interchangeably. So I wanted to bring up these old IUPAC accepted names. IUPAC accepted names. The first one that I already mentioned was methylbenzene, which is referred to as toluene. So it's Toluene. The next one that we're familiar with isn't hydroxybenzene. What do we call this one? Phenol. So phenol is the old-fashioned name. Instead of hydroxybenzene, it's very common to hear it just called phenol. There's one closely related to this, where we've got a methyl group coming off there, so we've got an ether essentially. So we could call this, I guess, what would that be? Methylphenyl ether. But the old-timey name that's stuck around is anisole. ANISOLE, so that's very common. The next IUPAC accepted name is if we have an amine. Some people will call this aminobenzene. The more common name is aniline. The next one, I'm going to scroll down, is if we have a carboxylic acid coming off of there. Does anybody have an idea what that might be called? Yeah, benzoic acid, and we'll cover naming of carboxylic acids later next term. So this is benzoic acid. The next one that's very common is if we have an aldehyde. What do you guys think this would be called? Benzaldehyde, yeah. The next one that's very close to these is the ketone derivative, specifically a methyl ketone. This one has kind of a weird name. Does anybody know what this one is called? It's acetophenone. It's called acetophenone because that methyl ketone is referred to as an aceto group oftentimes in chemistry, so we just call this acetophenone. And then the last one, which we saw back in our polymer chapter, is this alkene coming off there. Does anybody remember what this one is called? Styrene, exactly. So typically these are the parent names for these systems. And a good example of what I mean by this is, let's take an example molecule and try to name it. Let's say I've got this molecule. Yeah, just a second here. All right, so we've got this molecule here. What's the parent system? Toluene, right? The old system is called toluene. We could say methylbenzene. So what would we maybe call this? If we're starting numbering here, 1, 2, 3, 4, 5, 6. I would name this 2, 4, 6 trinitro toluene, or TNT, right? So that's where the toluene part of TNT comes in, is it's the old-timey name for methylbenzene. So this was an explosive, and we'll actually cover how to make this. Not that you would ever actually want to make it, because it would probably blow you up. But it's actually a pretty easy synthesis that they discovered in the late 1800s. Pretty useful. So now the next question is, why are aromatic rings so special? Why do we have a whole chapter dedicated towards this idea here? And the concept is a little bit strange to think about. So why are they special? So let's compare it to a normal alkene. Let's say we have this normal alkene and we want to hydrogenate it. So we can do hydrogen gas over a catalyst like palladium, and we can form cyclohexane. And if you do this in a bomb calorimeter, you can actually measure the heat of reduction here. And if you do this, the value is negative 120 kilojoules per mole. All right? Theoretically, we can do this, or not even theoretically, we can do this same thing with benzene. This time we normally have a nickel catalyst. Let me put this on the bottom. So we need 3 equivalents of hydrogen. We need a nickel catalyst, and it needs to be run at high psi. So in the top reaction, you can do that under pretty minimal pressure. The bottom reaction, we really, really have to crank the pressure on this. And if you do this, you can also get to cyclohexane. So what do you think the delta H value should be? 360. Yeah, we would expect it to be 3 times that top value, right? So we'd expect a delta H naught of negative 360 kilojoules per mole. The interesting thing is if you run this, the value isn't what you would expect. The actual delta H value for this one is negative 208 kilojoules per mole, which means this reaction isn't as exothermic. It's not as downhill as we had imagined, right? So then we've got to start to assess what's going on. There's some amount of energy that's being unaccounted for. Specifically, there is 152 kilojoules per mole of aromatic stabilization. Another way of thinking about this is it's so stable it doesn't react like normal alkenes, and we've already seen this. It's less reactive than normal alkenes, or even dienes for that matter. Last chapter we saw addition to dienes. We can't do addition reactions to benzene systems in that same way. So another way of thinking about this is if we had cyclohexene and we reacted this with bromine, we could get our brominated product where we add bromine across that double bond, and we would get an enantiomer. What if we did this with benzene? What do you guys think would happen? No reaction. Your natural inclination would be to say it should add that bromine across all of the double bonds, but the reality is these aren't like normal alkenes. They're very, very different. And so in this case, we get no reaction. And it's a little bit counterintuitive, but it has a lot to do with the electronic picture of what's happening in these systems. So let's get an orbital picture of what's going on here. So what I'm going to do is I'm going to draw benzene a little bit funny. So I'll take our normal 2D version of benzene and I'll say, well, let's lay it on its side a little bit. So I've got 2 carbons pointed in the back, 2 carbons pointed forward. So it's resting on its side. If we think about each of these carbons, are they sp3, sp2, sp? It should be sp2, right? Each of these carbons has 3 different bound groups onto it, not 4. So they'll be sp2, which means they've got a p orbital on them. So if I'm going to draw p orbital lobes sticking up. And then we've also got that other part of the p orbital sticking down. I'll give it some perspective there. There we go. And if we think about this, we've got pi bonds that can delocalize through this entire ring system. So these pi bonds, like we said very, very early on in organic chemistry, we said there's a resonance structure for benzene where these pi bonds can be delocalized. And we said that oftentimes people will draw the hybrid version, where instead of drawing them as a true single or double bond, they'll actually draw them as dash, because the bonds aren't really double or single bonds, they're more a bond and a half. And oftentimes you'll even see it drawn in books where people just draw that as a circle too. It's perfectly acceptable to draw it that way. But really, the reason that it's delocalized is we have all these orthogonal p orbitals where these electrons can delocalize all the way around the ring. And so these are really, really unique systems here. So let's discuss a little bit about how we can predict whether or not molecules are aromatic or not aromatic. And it's a little tricky. The rule that's really good at predicting aromaticity is called Hooples Rules or Hooples Rules, depending on how you want to pronounce it. I guess I don't speak German. Does anybody speak German? I don't know the umlaut pronunciation very well. All right, so the rule that he came up with was that molecules are aromatic if they have 4n plus 2 pi electrons. If they have 4n plus 2 pi electrons in a planar conjugated ring system. So essentially there's 3 different criteria we have to fulfill. The first one is we have to fulfill that 4m plus 2 rule. Second rule is it has to be planar. Third rule is it has to be in a ring system. You don't run into aromatic compounds that are linear. They just don't exist. So it has to be a ring of some sort. So let's take an example, and then it makes more sense if we look at it. I'm going to write down a bunch of molecules, and I want you guys to count how many pi electrons are in these. And this last ring I'm drawing over here is an 8-membered ring. All right, so this first ring, the square one over here, how many pi electrons do we have? How many electrons are in each pi bond? There should be 2 electrons in every pi bond, right? So we've got 2 pi bonds with 2 electrons each. So this one has 4 electrons in it. Does that follow the 4n plus 2 rule? If it has 4 electrons, where n is an integer?
What's n?
Yeah, what would n be to fulfill this? So n is any integer number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Can we fulfill an integer that satisfies 4n plus 2 to equal 4? So let's think about that. 4n plus 2 can never equal 4, right? Basic math, right? All right, not super challenging. So this one is not aromatic. if we look at it, your initial instinct would say, well, we could delocalize those electrons, but the reality is it doesn't follow the Hooples rules saying you need to have 4n plus 2 pi electrons. What about the next one? How many electrons are there? We've got 2 pi bonds. They each have 2 electrons. And then we've got this lone pair here, right? This lone pair could be in a p orbital too, right? This could be sp2 hybridized. So if we count all the electrons in those p orbitals, we've got 2, 4, 6. Does that follow 4n plus 2? Yes. So this one definitely can be aromatic. What about the next one over? How many pi electrons are in that one? 4, right? Because now we don't have a lone pair there. So in this example, we only have 2 pi bonds. This means it has 4 pi electrons, which means this is not aromatic. What about benzene? How many pi electrons does it have? 6. So if we take 4 and then make our N1 plus 2, that's going to be equal to 6. So benzene follows those rules. What about octacyclotetraene? How many pi electrons? 8. Is that aromatic or not? No, it is not aromatic. So if we think of these two are aromatic. And so they display that unique stability that we saw in the introduction, where we said that these are over 100 kilojoules per mole more stable than you would expect. They're surprisingly stable. It used to be a long-held tradition that these other molecules were called anti-aromatic. Well, they still are. And for a long time, it was always taught that anti-aromatic molecules are incredibly unstable and tend to degrade very quickly. It's kind of true, kind of not. They're finding out more and more that anti-aromatic molecules are incredibly useful because they want more electrons, right? If you're an anti-aromatic molecule, let's say we're the center one where you only have 4 electrons in there, it really wants another 2 so that it can become aromatic. These make excellent components to solar cells, because in solar cells you have to have a portion of your solar cell that absorbs electrons, right? So anti-aromatic molecules right now are really trendy for research, specifically regarding solar cells, but they don't have that inherent stability that aromatic molecules have. So it's a little bit more challenging to make a stable anti-aromatic molecule. It was something that we worked on a lot at the University of Oregon. One important thing to think about, too, that students often forget is, can we ever have an sp3 hybridized carbon in the ring system? What do you guys think? If we took one of these positions, I'll just say, I don't know. Let me actually draw an example of it below. Let me go with the cyclooctatetraene, but take away one of those pi bonds. Is this aromatic?
Yeah.
There cannot be sp3 hybridized carbons or hybridized atoms in the ring system. So if we look at this one, we've got 2 sp3 hybridized carbons, which means they can't be conjugated, right? We can't do resonance through an sp3 hybridized atom without violating the octet rule. So in this case, these are not conjugated, which means that this is not aromatic. This is something that throws off a lot of people when they're studying aromaticity, is they count all the electrons in the pi system, but then they forget to check whether or not every single atom is conjugated. It gets more interesting when we start throwing in non-carbon atoms into aromatic rings, and we're going to actually talk about that tomorrow. For the problem of the day, what I want you to do is to work on the top half. The bottom half we'll cover in class tomorrow. So try to complete the top half by tomorrow for lecture.